have Professor Alex Young, so who is the head of Department Anatomy and Medical Imaging and the principal investigator for ABI for many years. So he is the world leading researcher in cardiac imaging. I'm also claiming I'm a world leading researcher, but I think he's really. And he also the leading PI of the Cardiac Atlas project. Today we are extremely lucky to have him here to present his recent study of cardiac atlas research, the impact of machine learning on large-scale cardiac imaging studies. Yeah, thanks. Let's welcome Alex Young present.
Yes.
I will take the chair.
Yeah. Thanks very much. I was thinking, walking down here, that I was very privileged to be part of the initial group that led to ABI when there were about 4 or 5 of us in the old building, and thinking about the things that I used to do for my PhD. And some of you I know are doing PhDs and are wondering why on earth you're doing this. And I just thought I'd let you know that nothing's changed. Back in the day, one of the things I did was implement CMIS on a Unix system in '91. And another thing I did was implement a Lisp-style command line interpreter for image processing using Fortran 77. So I hope things have improved since then, actually. So I thought I'd start in the middle, maybe, with these risk scores. So until quite recently, this was the way that your GP used to evaluate you for cardiovascular risk when you rock up into the GP clinic, primary health physician. So they'd look at these things. It's hard to read. So this is no diabetes, non-smoker, smoker, blood pressures, cholesterol, and age. And these are the standard risk factors which we have built up over the years from large epidemiological studies like the Framingham Heart Study. And it's designed to put these dimensions into a simple chart. So me being a male or somewhere here and not a smoker and not a diabetic, I'm around 5 to 10% 5-year cardiovascular risk, which means there's an absolute risk of 5 to 10% that I might have a cardiac event in the next 5 years, which is a little bit high for my liking, but that's what it is. And you can see how it gets quite critical if you're diabetics and smoking. So this is above 30%. Actually, 1 in 4 of us are going to have some event like that. Something to look forward to. Unless we can do something about it. Nowadays, though, we're changing that picture, and partly due to new methods like machine learning. And this is a plot that came out of the MESA study, which was an update to Framingham using new biomarkers. And it was a random forest method, so a machine learning method, using about 150 markers to predict risk. And they did that by taking a bunch of people, about 5,000 people, in about the year 2000 and following them for 10 years. And the interesting ones that pop out, so this is the depth, minimum depth in the subtree. So if it's towards the bottom, it's a more important marker. And the projectors are really blurry, sorry. But this is age for death, of course. Your age is important. Next is TNF alpha and other biomarkers like NT-proBNP. CAC is coronary calcium score, and that's ABI. So if you're a member of ABI, you have a high risk. It's actually the ankle brachial index for pulse wave velocity. And these markers are much more powerful than the traditional risk factors, which are in red here. And so what we think is happening is that we're going one step back in the pipeline, you know. So from these kind of measurable risk factors, we're actually seeing something mechanistic happening to the physiology. The blue ones are MRI markers, and they cluster kind of in the middle of the traditional risk factors. Some of them are better and some of them are worse. And there's quite a few ECG ones as well. So this sort of thing is where we're going with risk factor analysis. The MRI markers are what I'll be dwelling on. These were not atlas-based ones. These are more traditional mass and volume ones. So I'll talk about the new methods for getting more information from MRI. So we've known for many years that the heart adapts its shape and function due to insults, due to environments, and also due to developing disease. And if you were a cardiologist, you could tell that this person had had a heart attack in this region where the wall is thin and not thickening very much. And the whole left ventricle remodels from a fairly normal physiology. Sometimes the walls get very thick and the cavity can get smaller, and that's known as a concentric hypertrophy pattern. Or the ventricle can become very large and the walls very thin, which is known as an eccentric hypertrophy pattern. And these have different risks for the different forms of events that can happen, heart failure or coronary artery scores. So several studies have been using imaging to try and add to the picture of how the heart mechanistically changes with these environmental and genetic and disease processes. So the New Zealand augmentation of this is called PREDICT, and it's run by Rod Jackson. And it's now captured most of the people in the North Island and maybe a lot in the South Island too. But there isn't any imaging in here. But we are capturing a lot of information in databases and following people and tweaking the Framingham risk scores. This is the MESA one that I talked about before. It had 5,000 people initially, and then they got 3,000 to come back for another imaging study at year 10. And this is UK Biobank, and they initially enrolled 500,000 people for clinical and blood biomarkers, and they project that they'll be imaging 100,000 of these participants by 2020. So back in 2010, we decided that we needed a mechanism for sharing imaging data between groups worldwide, and we established this thing called the Cardiac Atlas Project from initially NHLBI funding and then through a series of grants to keep it going. And we managed to get it as a officially recognised MESA ancillary study so that we had access to MESA information. And the Society for Cardiovascular Magnetic Resonance endorsed it. And we've now had about 50 groups worldwide using it for various things. Some of them have been data processing benchmarking, and some of it has been atlasing and trying to get an infrastructure and software tools out there for atlasing. And so the main studies that contributed were MESA. We had about 2/3 of the initial baseline cohort, and then this was another study in patients with myocardial infarction that they'd had a heart attack and they'd had one of those events which I showed in the first slide with the thinning of the wall and the regional wall motion abnormalities. And that paper that we wrote, I looked at it the other day, and it according to Google, it's had about 160 citations up till now. And we asked people if they're using the database to cite it as well. So that's how we track some of the uptake of the resources that we've got. So we did a few community-based sort of studies as well, and one of the most interesting ones was this one by Arvin, lead author in 2015. This was actually a really difficult study to do because we were trying to get at how people are analysing the boundaries of the heart in the different slices. So that's an apical slice, a basal slice, and a mid-ventricle slice. And we found that the different core labs were doing it slightly differently. And this has an impact when you're training algorithms for machine learning. If you get your ground truth from one core lab, you're probably going to be biased in some way relative to another core lab. On good images, people tend to get the same result, the same contours, inner and outer boundaries. They see it the same, but when you have partial voluming or motion or some sort of artifact, then you can be quite variable, particularly at the base where it's difficult to see where the valve is. And so we established a way of fusing these contours together in a consensus, and we use that for new people wanting to learn how to contour. They can download these cases and see how they compare with these values here. So these are the core labs, and this is ED, end diastolic volume, end systolic volume, and epicardial volume in mils. And you can see that every core lab is pretty consistent within themselves relative to the consensus at 0. But some overestimate and some underestimate in a consistent way, and that's just the way that they've been taught over the years by their PI, who says, I draw them like this, and if you don't draw them like that, you're getting them wrong. So everyone draws them like that. So we also came up with a way of checking out whether people were good readers or bad readers. So we took the logit function of specificity and sensitivity and plotted them on a 2D graph like this and draw distribution maps. And a lot of these readers are manual or manually influenced, but one of them, the SCR, that's the Symonds St, was entirely automatic and doing almost as good a job, maybe not quite as good as the manually based readers. We also did host challenges in other areas. So these are challenges run by other people, but are run through the data's available on the website. We did one on perfusion analysis, which is watching the blood wash in and wash out of the ventricle to get blood flow. We did one that was run by people here at ABI on regional stress and strain from tagged images. We did another one from a group overseas on motion tracking. And these are, although they're now kind of ongoing because people can still download the data and contribute results and see where they stand with relative to the previous people. So what we concentrated on though was ventricular geometry and function. That was left ventricle geometry. So you can automatically track the motion in the images using feature tracking in the short and long axis views, and then map them into 3D and fit this time varying shape model, which is just a finite element model basically of the left ventricle. And once you have that, you have parameters which are mapped according to their anatomical position. And you can use it for biomechanics, but you can also use it for statistical atlasing as well. So what we do is we take the images, we fit models, and then from the models we can extract statistical modes of variation. And these often are the modes which explain the most variance in the data. And you usually can get by with about 20 of those. So everyone's heart can be more or less well represented by 20 numbers. And then you can use those in classifiers using other machine learning algorithms to predict how your heart shape relates to certain conditions, like smoking and diabetes, or previous events. So to date, the main study that we've been involved with is MISA, which is called the Multi-Ethnic Study of Atherosclerosis. And they recruited nearly 7,000 people, not all of whom were imaged, but they were initially asymptomatic. So initially, they had no clinical evidence of disease. Turned out that some of them had heart attacks, and some of them were starting to get heart failure, and that was obvious from the MRI. However, self-reported, they were not aware of that at the enrolment stage. And they were aged 45 to 84 when they were enrolled. And they were initially free of apparent cardiovascular disease, and MRI was done on about 5,000 of them, and about 3,000 appeared for the follow-up at 10 years. So this is one of the interesting studies that summarizes the cardiac MR results. And I'll just go through this a little. It's an interesting kind of summary from the figure 1. So end diastolic volume for your left ventricle, this is age from 40 to 80, and this is mils, I think. And males tend to have larger hearts than females. Over time, though, the lines mean the difference between the baseline and the 10-year follow-up. Your end diastolic volume is going to decrease. More or less, as you get older, they found that they had smaller cavity, smaller chambers, and the same for females. But for mass, it's kind of a slightly different story. So for males, at least, the mass increased over that 10-year time. But there's a cohort effect in that the older people tend to have less mass than the younger people. And that is called a cohort event characteristic, and it's different from the longitudinal characteristic, which is the line segments from the baseline to the 10 years. And it can show that sometimes your older people have less mass because of other things going on, maybe in their childhood or diet growing up, than the younger people. Females didn't seem to change that much. So everyone's mass to volume increases, probably males more than females, because of this decrease in volume. And that means that there is some sort of hypertrophy going on, because the mass to volume ratio is a measure of hypertrophy as you get older. So this was like one kind of thing that came out of this study, and there's a lot of other interesting things that people have been publishing on. So when we ran that through our Atlas procedures, and then we corrected for height, we found that the statistical mode of variation that explains most of the shape in people is this one, which says that some people have bigger hearts than others. But that's correcting for their height, so there's something else going on there. And we know that in clinical studies, the bigger your heart is, the worse your prognosis is. So in epidemiology, small hearts are good. It doesn't pay to be big-hearted. The other mode that's popped out is this one, and we called this sphericity because it's kind of to do with whether your heart is more rugby ball or soccer ball shaped. And we also know from clinical studies that the more soccer balled your heart is, the worse your prognosis. So it was interesting that these two modes that came out of an asymptomatic population were related to these clinical indices, which doctors understand through literature of patients. So then we got a bit more complicated and used partial least squares regressions to figure out if there was a orthogonal basis that we could map everyone's heart onto that was actually related to things that clinicians understood. Because the other one was using a statistical method, principal component analysis, which has nothing to do with any previous clinical history about the field. So we use these indices which people know about: end diastolic volume, sphericity, ejection fraction, wall thickness, longitudinal shortening, and put that into an orthogonalization procedure which was using partial least squares to do a regression against shape. So if you regress everyone's shape against EDV, you get something like this, end diastolic volume index, which is corrected for body surface area. And sphericity looks more like this. And these are all statistically orthogonal as well. So that has nice properties when you're coming to do with fitting regression models for outcomes. And we were also able to map this onto the patients with heart attacks, showing that it's possible to get one mode by a procedure called information maximizing component analysis, which separates out the asymptomatic people from the people with heart attacks very well. And you can map that on as a percentile, showing that the asymptomatic people are around here and the people with myocardial infarction are around here. So where we're going with this is that if you turn up to a scanner and you can get your heart mapped, and then you can actually get a list of percentiles relative to different populations to show that you're on the 50th or the 80th or the 20th. But 5 years ago, when you came, you were somewhere else. So during that time, you've changed a bit, and we can quantify that now in a very mathematical way without having to go through these qualitative measures that people have been using up to now. So more recently, the Biobank in the UK has been really remarkable for setting a new benchmark in these studies. And they're recruited from an initial population of 500,000 people who were studied throughout the UK during 2006 to 2010. And they're asking people to come back for imaging. So they've already got a lot of information about genotyping and questionnaires. And since 2014, they've been doing not only cardiac MR, but also abdominal MR, brain, and carotid ultrasound, DEXA, and 12-lead ECG. And this is actually providing a huge amount of information. The cost for the MRI scan was actually very cheap. It was £90 for the cardiac MR scan, and how they got that cost down so much is that they didn't do it in a hospital or anything like that. They had a warehouse in Cheadle in Manchester where they were storing the bloods, and they just plonked an MRI scanner in it and got into a pipeline so that when you turned up, you had a questionnaire and then you got scanned through this kind of conveyor system. And you could actually do a scan every 20 minutes. And during that 20 minutes, you could get all this information. So they would get long axis, 4-chamber, 2-chamber, and that's called a 3-chamber with the outflow tract there. And lots of short axis as well, some tagging, that is, and a phase contrast flow through the aorta, a native T1 map at the mid-ventricle, and an aortic distensibility, all in 20 minutes. And we've been working with the first 5,000 cases through collaboration with Stefan Peterson but I looked on the site and there's about 30,000 nearly that have been imaged so far. So they're almost on track for where they said they were going to be, and on track for completion in 2020 or 2021. So what we did here was, for those 5,000 cases, we actually were able to use their core lab drawings around the contours and fit the models directly to that using an automatic pipeline. Kat Gilbert had an abstract at the conference earlier this year. And this was able to rapidly generate modes of variation in Biobank, which we could compare with the modes that we did previously for MESA. So we're just in the process of trying to compare the cohorts. They're quite different. So MESA was in the US, it was multi-ethnic. They tried to get a lot of different ethnicities. Biobank, the first 5,000 cases all came from Manchester, and they're almost all Caucasians. So we do expect to see some differences. But again, the main mode is the size, and the second mode is the sphericity. And the third one has to do with the orientation of the base. So you can again do the same trick with finding out what's correlated with, in this case, a heart attack, a previous heart attack. And you can generate mean shapes for people in a kind of healthy subcohort and those who have had a heart attack. And you can see that the tail is kind of long here. So there's a, the more you are towards this side, so your Z score is 5, you're in bad shape. We've also been doing this with the right ventricle, so biventricular models, and Kat Gilbert and Charlene Malger in our lab have been working this up. And we're applying it to congenital heart disease. These congenital heart disease patients are tricky because they have a variable morphology. So if they have two ventricles at all, it's unlikely that they look very normal. Some of them look fairly normal, but some of them are very strange indeed. So we had to come up with different templates to map those. And preliminary studies are showing that we can distinguish between different types of populations. So this is a study that Charlene's doing at the moment, looking at people with repaired tetralogy of Fallot. So they get repaired when they're babies, but they're prone to getting heart failure, particularly in their right ventricle as time goes on. And we think part of that's to do with the amount of regurgitation through their pulmonary valve. Some of them don't even have a pulmonary valve, and there's a lot of regurgitation. So you can actually map the shape related to pulmonary regurgitation. So this is the fraction here up to 50% from 0%. And this is looking from behind, and this is looking from in front. And there's shape changes that we can see, particularly in the right ventricle, so basal bulging and dilatation, but also in the left ventricle. So there's a diminution of volume, and the left ventricle is kind of with people with more right pulmonary regurgitation, the right ventricle expands and the left ventricle kind of gets squashed up.
How the hell do people live with 50% regurgitation? They must be short of breath all the time, aren't they?
Well, it must be tough. They often get tracked. So these sometimes people they're coming back every few years and they get an MRI scan, and the trick is to figure out when to put in a new pulmonary valve. So you don't want to leave it too late, because then your ventricle is not going to recover. But if you do it too early, then there's an increased chance of it going wrong later, and you have to redo it. And you want to reduce the number of interventions as much as possible. So at the moment, we don't really know when the optimal time is. It's something that we want to get a better handle on. These are people with just one ventricle. And sometimes it can look like a left ventricle, and sometimes it can look more like a right ventricle. There's different clinical criteria for determining what happens there, but some people are born with a hypoplastic LV or a hypoplastic RV, and the other ventricle just has to take over. And they do various operations to try and fix it, but they usually end up with just one. And we know that the people with the systemic right ventricle morphology do a lot worse, and their ejection fractions are certainly less, but they also have different shapes as well. So their ventricles are dilated, particularly in certain areas. And there's a student working on the relative strain indices for this cohort at the moment. Another thing that we're trying to branch into now is 3D echo. So up till now I've just been talking about MRI, and the problem with MRI is that it's usually only available at the tertiary institutions, and they cost a lot of money to run. So the hardware and software for 3D echo is becoming a lot more cheaper over time, and you can now get a portable device that will make models like this or hallucinate them to the data that you get here. And we're trying to map our atlases from MR to echo to try and get a cleverer way of fitting these models in a collaboration with Symonds. So I just wanted to switch gears a bit and talk about how the current wave of AI and machine learning is impacting on this space. And I'm sorry if a lot of you have heard of this before, but I'm not sure who's going to turn up. So I'll talk a little bit in general terms about AI, and then I'll talk about how it's impacting on cardiac imaging, and then I might, if I have time, go off tangent and go into wild speculations for the future. So what is AI? Well, people define it in different ways, but more or less it's if a problem is considered as requiring AI before it has been solved, that's what AI is. But once it's been solved, then it's considered data processing. Narrow AI is defined to be that sort of data processing that we're using in a restricted sense. So we know the domain, and we don't try and get out of that domain. So playing games, self-driving cars, image recognition. And it's the latest changes in the last few years have been driven by availability of data and availability of algorithms. So people are not being precious about keeping their algorithms secret. They publish them and they publish the code, and that's really been a major driver for the whole field, and faster computers. So back when there were competent people in the White House in 2016, there was this report which is an interesting read. Recommend that you can find this. It's free. Preparing the Future for Artificial Intelligence. But it's interesting to go back and see where it came from. A lot of the stuff that was done in the original game domain, like checkers, is similar to what we use now. A lot of this tree processing minimax algorithm was used in the original 1959 checkers program. The chess programs in the 90s were more kind of a lot of brute force, but some heuristics, and they've been recently superseded by the deep learning algorithms I'll talk to next. Another milestone was Jeopardy, which was natural language processing and clever figuring out of syntax. And then Go was an interesting one as well, because Go was considered to be so computationally intensive, it would just expand very rapidly indeed. But now, most of the best players in the world, I think, are algorithms. And more recently, Texas Hold'em, which is more of a game that requires bluffing as well, so strategies and things like that. And one that I like is determining whether Shakespeare or Marlowe wrote Shakespeare's plays. This is Marlowe and this is Shakespeare. They look kind of similar, don't they? But the consensus seems to be that they did actually collaborate on a few of those plays. So machine learning is that particular aspect of things which are looking at data analysis, pattern recognition, but are they're not trying to go from the bottom up in terms of getting a theory for signal processing. Instead, they'll try and learn what features are important for the problem as they go along. And one of the big things that's changed that field are these GPUs. NVIDIA used to be giving out these, so we wrote away for one a couple of years ago and it arrived in the mail, and that was a huge boon for our lab because otherwise it would have been weeks of training networks, instead it was hours. So these convolutional neural networks, or CNNs, are now pretty much the state of the art for a lot of image processing tasks. There's two flavors of them. There's the ones that do classification and the ones that do segmentation. And what they are is a bunch of layers which do convolutions. And the trick is that you try and learn what the weights are as you go along through an algorithm. And so the blue lines are convolution layers. The red lines are sort of condensing down to a lower resolution. And then you keep going down until you get kind of a latent space representation. And hopefully these are the features that you really are important for your process. And then if you're doing segmentation, you can go back up to get a similar resolution mask image which is your labeled image. If you're doing classification, then you just stop when you come out with a number, such as an ejection fraction. And I think that it's called deep learning, but I noticed Peter called it shallow learning, and that's a good label for it, because there really isn't much rocket science going on here. It's linear algebra and it's gradient descent. And the thing is that there's a lot of it. There's kind of a brute force approach. So we're still getting to grips with the mathematics of it, but it's hard to see often why these things are working and when they're going to fail. And neural nets, actually, I remember them coming on the scene in the early 90s, and they had the same problems then. It was hard to figure out what exactly they were doing and when they would fail. So in the heart space, this challenge was a bit of a game changer. You actually could get $200,000 worth in prizes in 2016 for segmenting the heart. And the winners actually ended up using a convolutional neural net, plus a few hacks, which they managed to just get above the rest of them. So what we did with our Titan GPU was train a VGG16 network to detect landmarks in the MESA study. And so this is a network that was done by an intern called Mark Jantz from Eindhoven. And he was able just to, in 3 months, download TensorFlow, install it, and get it working on our Titan GPU and train a network on about 2,000 cases, outputting landmarks. And you can see them here. They're the mitral valve inserts of the mitral valve to the ventricle in the short axis views and the long axis views. And these are old style images that were acquired in MESA in 2000. Nowadays they do it a little bit better, but we had to use the images that we had in these legacy databases. Some of them are really odd, so they have lots of odd artifacts, and their signal to noise is not very good. But the statistics on this is really the most impressive that I've seen for any algorithm to try and automatically do this. We also did it for the right ventricle inserts into the left ventricle, and from those landmarks and the contours we can then fit our models. So the networks we use for segmentation are based on the UNet, which is the standard at the moment. And we're using that to train our segmentation on our long axis images as well as the short axis images. And we also have a student working on tagged images. So this was done in Biobank as well. And they're much more complicated because you have to figure out not only where the heart is, but how to track these features. So we did it, Edward, for the first year of his PhD, or first few months actually, was just finding algorithms that would detect the heart first, so a bounding box to figure out where the heart is, and then from there try and use a recurrent neural net to process 20 frames and put features on the myocardium which would track with the tags. So because the tags change in every heart, they're in a different place, we decided to go for landmarks which were in the same anatomical position in every case. So for every case, this is the ground truth and this is the sort of predicted points. And it doesn't matter where the tags are, you get the same number of points in the same location. So where we think this is going in cardiac MR, at least, is summarized by this, which was constructed by Tim Leiner in the Netherlands for a paper we're writing, a review paper. And we think that the machine learning algorithms can really make an impact across the board. In image acquisition, you can use it to reconstruct images using less samples. So you're in the scanner for less time. And you can also use it to automatically process the data, generate reports, and also generate these Z-scores that will map the prognosis of the patient. And so it's going to have an impact across the board in the future, I think. So just for the last couple of minutes, I thought I might just go off-piste a bit and natter on about some of the things that have been popping in my mind as I wrote this talk and over the last couple of years. So used to be, until about the 1960s, computers were people. And this was a great movie. One of the stories in this movie was how these people retrained themselves because they knew that their computer lives were going to be overtaken, so they became programmers. But there's this interesting YouTube video which has been available for several years now called Humans Need Not Apply. And the idea for this is that just as the Industrial Revolution didn't really make better jobs for horses at the time, you remember that the steam engine came along and we don't really think of that as making better jobs for horses. We shouldn't really be thinking that this sort of technology is going to make better jobs for humans, because for humans read chimpanzees, and often with these applications it may not be better to have the chimpanzee in the pipeline. And the pipeline might work better without the chimpanzee altogether. And radiologists in particular have been a bit defensive about this because their business model runs as a service. So they're a physician, but they don't actually see patients directly, at least often. So they run as a service, and there's a physician who sees the patient and they ask for a report. And the report can come from a radiologist or it can come from a machine. And the Turing test for radiologists would be, can you tell the difference? And I've noticed that there's been a lot of discussion in the radiology world about how or why they're going to cope with it. That they're worried because not because of radiology in particular, but because of the people who sit on the boards of hospitals who are interested in the economics, and if they see that some algorithm may be able to replace a few radiologists, then they say things like, well, we don't need to train so many radiologists in the future. And that's what's worrying them. But us engineers shouldn't be so complacent either, I think, because we could probably replace a lot of what the engineers do at the moment in the MRI space, because a lot of the engineering for MRI machines is built around making good images that people can look at. So if you replace MRI, magnetic resonance imaging, with MRAI, then you don't need to make images at all, and a lot of that hardware you can actually put in better ways. So the cost of the hardware may fall, and you put quite a few engineers out of job, I think. But so the summary, I think, is that this current wave is making an impact in a lot of activities in MRI and cardiac imaging as well. But this is a good quote that I found from 2017. Natural stupidity rather than artificial intelligence remains the greatest risk. There's a lot of inbuilt bias into algorithms. It was recently found that the algorithm that was used in, where was it, Amazon, to triage CVs was throwing away a lot of female CVs because that was the bias that was built into the algorithm. When no one actually built it in themselves, but it would just appeared because of the training data that they were using. So I was encouraged by reading this book, which I highly recommend. It's called Darwin's Dangerous Idea by Daniel Dennett, one of the great philosophers of the modern age. And his thesis generally is that the design space that we are working in as engineers is in effect the same design space that has been imposed on us by natural selection. And so the natural selection process of optimization that produced us is also the same one that's going to produce the general artificial intelligence that are no doubt coming. And it's just part of the same design space. Okay, so I'd like to thank the collaborators in Auckland. There's a lot more than there are on here, and PhDs and interns, and also our collaborators in UCSD who are working on in the congenital aspect of the project. Thanks very much.
Any questions?
Two. First was, you didn't mention anything about wall thickness, so I'm presuming that actually the sphericity shape was actually as good an estimate as on its own as wall thickness with any of those. Is that correct?
It's in there. It's harder to pick out, but we do see it when we look at the change from end systole to end diastole. So if you look at these functional modes rather than the end diastolic mode on its own, then you see that one of the big ones there is the shortening and the wall thickening. Yeah.
The second, no, should really double up on questions, but anyway. What about assessment of fibrosis using late gadolinium enhancement and or T1 imaging? Are these things that you're also looking at?
Yeah, well, the data for that are less available, so they didn't do it in MESA. They did it for the follow-up for some of them. So I think they had about 1,000 cases there, but we haven't had time to look at those yet. And they didn't do it in Biobank because they didn't want to inject the contrast. The contrast does have adverse effects if you have poor renal function, and they just didn't want to go there for the ethics. So, but yes, So there are good work being done on detecting scar and T1 mapping. Yeah. Mm.
So how far down is torsional motion in your list of significant modes?
It's nowhere in this because we haven't captured it. So what we do with these shape models is we fit these models to the cines, but we don't have the torsion. We can get that from the Biobank because they did three slices, but we don't know the prognosis of that. But we do know from clinical studies that torsion is very important. Yeah.
Thanks for that. So have you, with the shape analysis, have you done a separate analysis on the shape with having the size of the heart normalized? Because I saw that the first one was the size itself, so which is kind of obvious, but if you remove that, would it be possible that you would see other,
Yeah.
you would capture other variability?
Yeah, yeah. And the way that we were trying to do that orthogonalization process, it would we chose EDV, but you could choose ESV. That's also a good one. And then you Graham-Schmidt type subtract that mode out, and then you're left with the rest. Yeah, and then you carry on like that. The order is important, so you have to figure out which order that you're doing it in. But for the initial ones, we didn't want to take out the size because we knew that that was a big factor for prognosis. Yeah.
So see like us, if we want to access the biobank, so how hard say we plan to access? How?
It's a procedure that you apply. They have a fee per application. I think it's £2,000, and then there's a backlog, so you have to wait for a few months. Yeah, but the nice thing is that you can ask for as much imaging as they have, so you could apply for the 30,000 cases.
Right. Also, I saw you have one slide showing segmentation. You use UNet do segmentation for the left ventricle. So your segmentation, you only do the cavity, or you also just do get the left ventricle tissue?
No, there's several labels. There's the left ventricle myocardium, the left ventricle cavity, and the right ventricle cavity as well, which we do for Biobank because we have ground truth for that.
Oh. So you do all segmentation at one go, so different label.
Well, that's the approach that we've tried. Yeah. Multi-label. You had another one.
Oh yeah, just a quick one with the RNN that you were tracking the tags. For the input vector, did you guys just use the pixel position in the image? Was that the only information for the RNN?
Yeah. So the RNN works on the cropped region, but the cine. So we put 20 frames in, so it becomes like a 20-channel image, and then it's a combined CNN RNN thing.
Okay.
Just wondering, have you looked at preserved ejection fraction hearts, and is there a particular shape to them?
We haven't yet, no. We had a student lined up for that, but they didn't turn up in the end. But we have been involved in a study with Mark Richardson in preserved ejection fraction heart failure people, and it'd be really interesting to find an atlas for them. The trouble is that it's very much a catch-all for lots of different pathologies. So the ejection fraction is what they do to put them in that bin, but there's a whole lot of different things that are happening.
Alistair, I would like you to comment and a bit to speculate on possible ways to try to reconcile all this data processing new age of deep learning with the physiological modeling community. We know that for a lot of years it was quite apart, like modelers and data processing people not talking a lot together. Then at some point it looked like, okay, let's go to personalizing models, etc. It looks like this deep learning is going to pull apart again these two communities because of these black box things of deep learning,
Well-
and the other set of the spectrum, more physiologically oriented things?
I view them, this is another tool that we use to feed into the physiological models. So I'm really happy that I don't have to sit and draw red circles around the images anymore or track the tags, because I spent a lot of hours doing that. And so that part, I can see that people's jobs get easier that way. But where it comes interesting is that when you just feed in the images and you pop out a map of where the reentrant loops are predicted to be, and you don't really know what's gone into that. So I think that there's interesting work being done on trying to put the physics in. So they're just using this technology to solve the physics faster. So rather than do a complicated nonlinear iteration process to optimize it, you run it through a network which has kind of learned how to process that space and give you a reasonable hit on where the parameters should be. But so doing the same physics but faster. So CFD is a good example of that, right? So we know the physics of CFD, but it takes a long time. And reconstruction of images also, it's a very painful process to iteratively reconstruct images.
You made the point that imaging quality could be reduced, which probably is true, but won't you get better results of the kind you've just been talking about if you have higher imaging quality? I mean, certainly that's going to be true of a number of the things which we can't even see in MRI at the moment.
Yeah, and trying to figure out which signals are important, that's the hard part, yeah. But you can imagine that there's a company in Wellington, Magritech, that do little MRI devices with small magnets, and you just hold it up to someone and take data. So that's where we could be going, you know.
Are you doing it where? Alistair, the university? Or?
Well, it's Paul Callahan's company originally. Yeah, I'm sure they're working in that space. They're trying to, yeah.
So if I may, so another thing that it's quite common problem for both physiological models and even deep learning, just to handle difficult cases and abnormal cases. Sometimes we show that models, or physiological models, any model can kind of capture normality or regular abnormal patterns, but then a new case, really abnormal one, like the single ventricle tetralogy of Fallopian. These are very, the most difficult ones to model, but the most interesting ones at the same time.
Yeah, yeah.
So, I mean,
yeah.
the amount of cases you need to build a network or even to validate a model like this is not obvious, right? I mean, for this type of applications.
Yeah. So I think what I'd like to see is the ability to expand the space that you can characterize on the fly with someone who's saying, no, you got that wrong, it should be here, and it immediately goes back into the algorithm underneath rather than waiting for a lot of cases to build up and then retrain it. So that sort of on-the-fly learning, I think, is going to become available next generation. So you don't ever stop learning. Yeah, there's interesting things to do with transfer learning as well. So you train it on a big data set and then you try and push it towards a refined data set with just a few cases. So with Biobank, we've trained a lot of networks on Biobank, but we find that it works really well on Biobank cases. But other scanners, even, they can really throw them off in unpredictable ways. But just including a few of those cases will fix it.
If no more questions, then let's thank to Alex Young for his fantastic talk.
Thank you.
Copyright University of Auckland, all rights reserved. The content and delivery of lectures in this course are protected by copyright. Material belonging to others may have been used in these lectures and copied by and solely for the educational purposes of the university under license. You may record the lectures for the purposes of private study or research, but you may not sell, alter, or further reproduce or distribute any part of these lectures to any other person. Failure to comply with the terms of this warning may expose you to legal action for copyright infringement by the copyright owner and/or disciplinary action by the university.